So in the previous videos, we derived the expression for the wave function, which means the solutions to the hydrogen atom, but we didn't really get the chance to do much with them. So in this video, that is exactly what we're going to do. We're going to familiarize ourselves a little bit with the solution that we found, and more concretely, what we're going to do is we're going to determine some of the first wave functions of the hydrogen atom using the formulas that we found in the previous videos. Now, it is important to say that these recursion, because let's just remind ourselves of the solutions. So the total solution of the wave function, this psi, it depended on three numbers, n, l, and m, and this was just the product of some function that depended on r and some other function that depended on theta and phi. Now, this first function we determined was this radial part, which depends on n and l, and the angular part we saw are the spherical harmonics, and it depends on l and m. And now I really want to emphasize that, that it's really important that you do the exercises that I'm going to do in this video, which is basically just to use these formulas to determine some of the hydrogen atom wave functions, because it really helps you understand these formulas better. Now, what I wanted to comment is that we saw that these were the expression for r and these spherical harmonics. So for r, it was 1 over small r e to the minus small r n a times small r n a to the l plus 1 power times some function v that depends on, we used before this rho variable, which we can then transform into r, and that's actually what we have to do because this has to depend on r in the end. But I left it as rho because that's what we saw in the previous video. And we saw that these polynomials, which were the Laguerre polynomials, could be determined using this recursion formula right there. The thing is, this is not all that comfortable to use. We will use it for now, but as you can see, it is really not all that nice and it can be somewhat confusing. So there exist some generating functions that actually tell you what these polynomials are, and you can, it's basically just a formula with some instructions. It's not a recursive formula like this. You just go ahead, plug n and l in, do some derivatives, and you get the result out. However, we didn't derive that, so I don't want to use it. I just want you to know that they exist, and that's actually what they usually tell you in the textbooks, because it can be easier to work with than this. But once again, the derivation from those expressions is kind of more for mathematics courses that it's really not all that interesting for us. So as there exists the generating function for the Laguerre polynomials, which is basically what you find using this recursion formula, the same exists for the Legendre polynomials and the associated Legendre polynomials. But I'm sticking to the formulas that we derived. Now, in the last video, we ended with this expression right here. However, there is a way to make this a little bit simpler. Because remember, in the previous video, we saw that this number n could be related to this amount rho. And in fact, what we saw is that 2n is going to be equal to rho. So we can actually use this in here to get rid of this rho, because this is just some constant, and n is something that we can actually work with. It's much more intuitive because, as we saw when we analyzed the energy expression, n is related. In fact, it tells us the energy level that we are dealing with. So instead of writing this as minus rho 0, I'm going to write it as minus 2n. But now that we did that, we can just factor this into this parenthesis right here, so that this will be somewhat easier. So we get plus 1 minus n. Okay, so that's just a way to write this expression that is much more comfortable to use. And finally, I just want to remind ourselves the expression for the energy that we found previously, which is this formula right here. And if we evaluate this and just see, well, the lowest energy here, it will be n equals 1. That's going to be the state for the, this is going to be the ground state of the hydrogen. And so we just call this right here E1, and we just divide it by n squared to determine the energy for any level that comes after that. So those are the main formulas here. So given that introduction, let us now actually begin calculating some of these states. Let us begin by going for the ground state, which is when n equals 1. So the first thing that we now need to think about is, okay, so n is 1, what are the values for L and for M? So remember, what was the condition for L? Well, L, what we knew is that it can be any value up between 0 and up to n minus 1. But in this case, n is 1, so n minus 1 is also 0. So for the ground state, L can only take the value 0. And what happens with M? Well, we also discussed the values that M can take. M can go from minus L to plus L. But L is 0, so this is just 0 as well. So this means that the ground state is going to be the state 1, 0, 0. Remember, this is n, this is the value for L, this is the value for M. And now you might be wondering, well, we know that n tells us the energy level. What do L and M tell us? Well, for now, we can't really answer that question because, well, with what we have seen so far, we just don't really know much about it. But we will see later in the course, when we actually start working with angular momentum, that we will find out much more about these two quantum numbers. So for now, we're just going to be working with them, and later we will actually understand them better. So this wave function will be the product between the radial part, which, remember, depends on n and L. So this will be R10, and these spherical harmonics for the case L equals 0, M equals 0. Okay, so this is going to be our wave function. And there is one last thing that I want to comment about the formula that we are using for the spherical harmonics, because there is actually a convention that we need to discuss. So this solution here is quite correct. However, there is an epsilon here that is included in most textbooks, and its value can vary a little bit. And why is this included? It is included because, as I said, we will work a lot with these spherical harmonics and these sort of spherically symmetrical potentials in the section dealing with angular momentum. So there it's going to be convenient that we take this epsilon to be 1 if M is greater or equal to, sorry, the other way around, smaller or equal to 0, and that we take it to be minus 1 to the mth power in the case where M is greater or equal to 0. So that is the convention that is taken here. So we're just going to calculate this, and at the end we have to remember to take into consideration the convention for this sign. Okay, now this is what we have to calculate. Then let's begin calculating the radial part. In order to do that, let's take actually all of this right here. So I'm going to go to the next page here, just to make sure that here we are dealing exclusively with the radial function. So what is the radial function for n equals 1, L equals 0? Well, it's going to be this evaluated at those values. So R10 is going to be 1 over R, e to the minus R divided by n is 1, so just a. Then we have R to the NA to the first power, so just R divided by a, because n is 1. And then we have this V that is a function of R. Before we saw it as a function of rho. So here, the first 3 times, don't be confused, we'll have to substitute the value of rho in terms of R. Okay, so here we can just simplify this R with this one right here. Okay, so this is what we have so far. Now, well, there is still the issue of calculating this V function, so let's do that. Now we know we can determine it from this recursion relation, and very, very important, how do we do this? Now this is where it can get tricky. We know that in order for these solutions to be normalizable, we need there to be a top value for these coefficients, because remember, just as a quick reminder, these V of rho, or of R, depending which variable you're using, we defined it as rho, that's why I'm sticking with it for now. We said this is going to be the sum of j equals 0 to infinity of some coefficient times some power of rho. So we're going to have these polynomials right here. And we can't let it grow forever, otherwise it would not be normalizable, and we need it to be normalizable in order for this to make physical sense. So that means there has to be a top. We discussed it in the previous video, I'm just reminding us here. We need to have a maximum value of j, because j is the one that determines the coefficient. That's just to make sure that you're not confused if it's a maximum value of L or N or whatever. It is j here that tells us there has to be a maximum value. And that means that at that maximum value, this thing right here will be 0. So j max, all of this, so plus L plus 1 minus n, this has to be equal to 0. So this means we can determine the maximum coefficient in terms of L and n, and that's exactly what we want to do. So j max, this will be n minus L minus 1. And what are our values this time? Well, n is 1, L is 0. So our maximum value for j will be 0. So that means if we plug in j equals 0, this is already going to terminate. This series will terminate. So let's do that anyways, just to make sure that we understand it. So let's plug in j equals 0 in here. So we get a1 because j plus 1. This is going to be 2 times j is 0, L is 0, 1 minus 1. So this is times 0 times a0, and well, divided by all of this, but it doesn't matter because it's going to be 0. So a1 is 0. This means the only term of this sum that is not 0 is a0. So our v rho is going to be a0 times rho to the 0th power, which is just 1. So we can just write it like this. So this is our solution here. Let us plug it right here. And in this case, it doesn't really matter because there is no rho, so we don't have to worry about changing the variable back, but we will have to do that later. So just multiply this by a0. So this is the solution for our radial part. Please notice this is not yet normalized. That is how we determine the value for a0, but we will do that in the end when we also normalize the spherical harmonics. So that's what we're going to do. But before that, as I said, we need to find the angular solution. So let me just go ahead and copy all this. Okay. Now, so we know this right here is going to be our angular solution. We need to determine these polynomials here, which are the associated Legendre polynomials. What is their form? Well, it is 1 minus x squared to the absolute value of m divided by 2 power, and then the mth derivative with respect to x of the Legendre polynomials. And how do we find the Legendre polynomials? By using this recursion formula. So let us use this right here. Now remember these coefficients, because just as a quick reminder, this 2 was a power series, so it was of the form j equals 0 to infinity. Please don't confuse these a sub j with the ones from the radial equation. Okay, so they are just completely different. These are part of this Legendre polynomial, the other ones are part of the Laguerre polynomials, right? One is from angular part, one is from radial part. Okay, so these are also some coefficient times x to the jth power. And as we saw, in order for this to be normalizable, the series has to end, which means if our L is going to be odd, we can only have odd values of j, so that at some point j and L are equal and this coefficient terminates, and then there is nothing more. So in this case, what is L? Well, L is equal to 0. So j can have a maximum value of 0. So that means that a 0 plus 2 is just 2. a2 will be, well, 0 minus 0, so just this is going to be 0 times a0. So the only term that will be here is going to be a0, similarly as before. So PL of x, and not any L, right? This we already saw. This is for a particular value of L, which is P0. This will just be a0. And now, because we already used this a0 name, actually let us write this as big A, just to make sure that there is no confusion with the radial part. Just big A, because they will both come into the same equation, so I just want to make sure it isn't too confusing. Okay, and there might be some confusion as to, I mean, don't forget about this first term. Okay, that is a very common mistake, because we begin looking at the first term after the actual first term, because this is a recursion formula that tells us some term and it depends on the previous one. So just because a2 is 0 and that is the first term that we are calculating, that doesn't mean that the first term of the series is 0, because the first term is just a0, period. That is and there's nothing more to do. So the one that we are calculating is the second term. So please, please, please don't make that mistake. Don't get confused on that. So now we know P0. How do we find the associated Legendre polynomial? Let's take a look at this. So this is just take this to the m divided by 2 power, but m right here is 0, so this to the 0th power is just 1. Then take the mth derivative, but m is 0, so basically don't derive it at all. So all that we're left with actually is that this is going to be the same as its associated Legendre polynomial. And the final step is that when we plug it into the spherical harmonic formula, we have to replace every x for cosine theta. But in this case, there is no x in our formula, so it doesn't really matter. Now, let us go ahead and plug this into the formula. So y0, 0 is going to be some constant. Notice we have a constant of integration here and here, so we might just combine them into a. It doesn't matter, it's just some constant of integration. And then we have, well, we combined this a with this associated Legendre polynomial, and then we have e to the I m phi. What is m? M is 0, so this right here is just 1. And then we have this epsilon. Well, when m is 0, this is just 1, right? Because for this convention, whenever m is greater or equal to 0, this is 1. So when it is so this is smaller or equal, and when it's greater or equal, it's minus 1 to the mth, but either way, they are the same. You get 1, right? That's why both of these cases include the case m equals 0, because it's the same. So this means epsilon is just going to be 1. So that means our spherical harmonics is y0, 0. Okay, let us now go back and plug it into our formula, which we had right here. So what was the radial function? We have it, let's see, right here. It's just small a0 divided by a, e to the minus r divided by a. And now let's multiply this by the spherical harmonic, which was just some constant a. Now this is technically correct, but this is not normalized. And now just a quick reminder, this a right here is the Bohr radius. This is just a bunch of constants multiplying each other, so that's actually not what we're going to be solving for when we normalize, just to make sure that you're not confused, because there's a lot of a's right here. So how do we normalize this? Well, that means normalizing just means we take this square of this absolute of this modulus of our wave function, and we want to integrate it over all of space. Now, how do we do that? Remember here, well, we are going to be dealing with spherical coordinates. That means we have to integrate the r, this distance, from 0 to infinity. We need to integrate theta from 0 to pi, and we need to integrate phi from 0 to 2 pi. And another classic mistake, in fact I did it myself when I took this course, so please don't make this mistake. I actually failed an exam because I had to do a question regarding to this and I forgot to do it. We are integrating in spherical coordinates, so you have to include this r squared sine theta. Please do not forget that. That is just because we're integrating in spherical coordinates. So this is going to be, well, let's see, the first integral is the r, the second one is the theta, the third one is the phi. And we can actually separate this into two integrals, and well, this has to be equal to 1, obviously. We can separate this into the radial part, which is just integral from 0 to infinity of, well, let us put in the value of this actually, just to make sure that I'm not getting ahead of myself. So I'm going to move this. Oh, I intended to move the r too. So what was our wave function and what is it squared? Well, that's just going to be a0 squared, small a, big A squared, e to the minus 2r a. Okay, so now let's separate everything that depends on the radius and everything that does not. So I'm going to do it down here. Now, so 1 has to be equal to the integral from 0 to infinity of e to the minus 2r divided by a r squared dr. And we can also leave this a0 squared attached to this integral because that is the constant of integration that we want to find when normalizing the radial part. And well, we can also leave this divided by a squared here. And then we have integral from 0 to pi. And well, I reversed the order here, but it doesn't matter because there is no cross dependence. 0 to 2 pi. And then we have big A squared sine theta d theta d phi. Yes, and this is multiplying. So now we have two integrals that we want to solve. So we want to solve the radial part and the angular part, and each one of those has to be separately 1. So let's do that. Let's begin with the radial part. Obviously, you can begin with whatever you want, but let's do it like this. Okay, so let me move this. Okay, how can we solve this? Well, just to make it a bit cleaner, I'm going to write it like this, a squared. And now this is an integral that you have to solve integrating by parts. So let us, well, the easiest way to, you don't have to do it, but what I would do is say, okay, let's just say z is going to be defined as r divided by a, because we have r divided by a here and same here. So we get rid of some of the constants. It's not obligatory for you to do it, it's not mandatory, but it's actually going to be nice. You know, it will be less constant flying around. So let's make the substitution. dz is going to be dr divided by a, so dr is going to be a dz. So when we do that, we get a0 squared integral from 0 to infinity. The limits are still the same because when r is 0, z is 0. When r goes to infinity, so does z. And then we get e to the minus 2z, and then we get times z squared dz times a. And the a we can just write out here. Okay, so let's solve this by integrating by parts. So let's take u to be the, u is going to be z squared, du will be 2z dz, dv will be this exponential e to the minus 2z dz, and v will just be minus a half e to the minus 2z. Just because when you derive this, you're going to get this right here. Okay, so now let's apply. So this integral will be a times a0 squared factor of, so these two multiply, so we get minus z squared divided by 2 e to the minus 2z evaluated between 0 and infinity. But let's take a look at this. So when you evaluate at infinity, this term right here goes to 0 faster than this goes to infinity. So when you evaluate it at infinity, this is just going to be 0. And when you evaluate it at 0, this is 1 and this is 0. So basically this term is just 0, right? In both cases, so it just goes away. And then we have minus this times this. But this already has a minus, so we can just write plus 1/2 times 2, because there's a 2 there, integral of 0 to infinity of z e to the minus 2z dz. So this right here, these two will cancel out, and now we have to integrate by parts once again. So we can just say, okay, so u will just be z, du will be dz, dv will be e to the minus 2z. This is the same as before. And then we get that v is just going to be minus 1/2 e to the minus 2z. So when we put this into the integral, we're going to get the first part will be z times this right here. But just as before, this will be 0, because at infinity, the exponential goes to 0. At 0, this will be 0. So we are only left with the second integral, which is minus this times this, but once again there's minus minus, so you get plus. Then there's going to be 1/2 integral of from 0 to infinity of e to the minus 2z dz. So now when we integrate this, we're going to get minus 1/4, because 1/2 from here and 1/2 when you integrate this, times e to the minus 2z evaluated between 0 and infinity. But at infinity, this goes to 0. So the first part will be 0. So we get minus 1/4 times minus 1. So this will just be 1/4. Okay, so now let's go back and plug it in, because this integral was actually this one right here. So it was multiplied by a and a0 squared. So this means the integral that we were solving was a0 squared times the integral right here. And actually this has to be equal to 1. And the value for the integral that we found is just 1/4. Okay, so this is actually what we need. From here we can find a0 squared is going to be 4 divided by a. And this means that a0 will be 2 divided by the square root of a. So here we found the first normalization constant. Now let's go ahead and solve this right here, which is going to be the normalization for the wave, for the angular part of the wave function. So this also has to be equal to 1. Now the phi integral is going to be quite easy, because we can just write it. Wait, I need to invert the integrals because this one is for theta. So let me write it like this. I'm not changing anything, I'm just reversing the order here. So integral from 0 to 2 pi d phi, integral from 0 to pi d theta. Okay, because phi is the one that goes from 0 to 2 pi, and this integral, well, that's just 2 pi. You're basically integrating 1, which is just going to be phi, and then you evaluate it at 2 pi, which is just 2 pi. So we have to solve this right here. Now this is also quite simple. We get 2 pi times a squared times the integral of sine, which is just minus cosine theta, and we have to evaluate it between 0 and pi. Well, that's just going to be 2 pi big A squared times minus cosine evaluated at pi. Cosine of pi is minus 1, so we're going to get plus 1. And then we have minus, but there's also minus here, so that's going to be plus cosine evaluated at 0, which is just 1. So we're going to get that this is going to be 4 pi a squared, and this has to be equal to 1. So a squared is going to be 1 divided by 4 pi, and you can just see here that a is then going to be 1 divided by the square root of 4 pi. Now let's put all of this back into our wave function. Now let me see, where was our result before? It was right here. So what is the value for big A? Well, maybe let's begin with small. This a0, I think it was square root, no, it was 2 divided by the square root of a. I'm gonna make sure because I do not trust my memory. Let's see, yes, 2 divided by the square root of a, and then big A, this is 1 divided by the square root of 4 pi. And now we multiply by everything else, so times e to the minus ra divided by a. And well, we can write this a bit more compact. Let me just go here. So psi 1, 0, 0, this is just going to be, well, this 2 will cancel out this right here because square root of 4 is also 2. So we get 1 divided by the square root of pi times a cubed, which is because we combined these two a's. And this is going to be times e to the minus r divided by a. So here it is. We now determined the first, this is the ground state, which is basically n equals 1 of the hydrogen atom. And as you can see, well, its energy is just going to be this formula right here, but for the case n equals 1, which is just E1. And if you plug this in the numbers here, the energy of this first state is just minus 13.6 electron volts, which is exactly what was expected from both a theory that was before from Bohr and the experiments that have been held. Now, I took a bit more than I thought doing this, so I'm going to pause the video here and I will make a second video where we will find psi 200, psi 210, and psi 21 and plus minus 1. So that's what we're going to do in the next video. I will see you then.